In this final neural networks lecture, I will highlight a few special neural network structures which are popular in the current research community. The probably most popular neural network architecture is the convolutional neural network, or CNN, also known as ConvNet. The CNN is a further development of the neocognitron, which was a computational structure developed by Fukushima, which again was modeled after the Hubel and Wiesel model of the primary visual cortex. The principle of a CNN is somewhat comparable to that of the SIFT algorithm. It has a layered structure. Typically, a CNN has a convolutional layer, followed by a max pooling layer, then again a convolutional and a max pooling layer, and so on. A convolutional layer contains a number of filters, for instance of size 5 times 5 or perhaps 12 times 12 pixels. Each filter is matched on the original image from top left to bottom right. The resulting match leads to a new image for each filter. This is done for all filters in that layer as is shown in this figure. Then, on the resulting images, a max pooling operator is performed. This max pooling, typically of size 2 times 2, subsamples the image by selecting the largest value in a 2 times 2 window. As said, the structure can then be repeated, usually 2 or 3, sometimes even 4 times. On the last layer, one typically adds a feed-forward neural network to do, for instance, image classification. The great results that CNN obtains in the last few years are a result of the fact that the filters are learned from the training data rather than devised beforehand. Here some learned filters are shown in a 2-layer CNN. For instance, in this picture, the CNN was trained on faces only. The bottom filters learn to select things like eyes or noses, etc., while the filter in the next layer combines these together to form prototypical faces. When trained on natural images, the first layer typically performs line detection, much like the one finds in the visual cortex in V1. There also exist different CNN architectures, and often even the max pooling operation is not used. When you look at the literature, you will find that CNNs are amongst the most used neural networks. Also, companies like Google use them for image classification. Note that there are no rigorous mathematical descriptions of CNNs, and further development is mostly a matter of trial and error. Now to a different structure. All of our previous slides have discussed the use of neural networks for labeled data. In all instances, we assumed a dataset X, Z. But what happens if we do not have these labels? Even though a later lecture will focus on the general problem, here we will discuss how a neural network can be used in this case. So consider this neural network. We have an input layer here, and we want to use this neural network to map our x's on z's. But we don't know the z. The autoencoder is a specific neural network to deal with this situation. We use a neural network to find z by itself. We stack another mirrored neural network on top of the first and ask the top neural network, the decoder, to give us back x. So this structure, which is just a neural network in itself, is trained to map x to x, but pass that reconstruction through a so-called latent layer, which has fewer neurons than the input or output. This autoencoder thus learns to create a dense representation in latent space. This model from the 1990s was difficult to train back then, but now it is a very successful methodology to do unsupervised learning. Especially recent improvements on the autoencoder based on variational inference has made this to a very useful model which can be used to do dimensionality reduction very efficiently. We will shortly explain the variational autoencoder in the lecture on supervised learning. Recurrent neural networks extend feed-forward neural networks by adding weights between the neurons within each hidden layer. Thus the system has an internal state, and a recurrent neural network can be used to represent time series. Training of an RNN is very similar to normal neural network training. Here, however, we have to roll this out in time. We start by inputting x at time step 1 to compute the hiddens, and then we input the next x, and so on and so forth. After the last one, we start computing the residuals by comparing the output with z, capital T, and then back to z1, and propagate the residuals through the recurrent neural network. Finally, we use the summed residuals to update the weights. RNNs are being used for speech recognition, text recognition, as well as generation, also for video annotation, for instance. Also, modern machine translation is mostly based on RNNs. And then, of course, they play an increasingly important role in robotics and start being explored for process control. As a last topic, we want to shortly touch upon probability theory and neural networks. We will not discuss variational inference in this lecture, but we'll still look at a probabilistic version of a neural network. Why? Well, for one thing, it is quite important to have a system not only predict an output, but also give a confidence interval for that output. With GPs, Gaussian processes, you have seen another model which does that, but then GPs only base their confidence interval on the amount of data that is available and not on the stochasticity of these data. The basic principle of such neural networks, which have been developed from 2013 onwards, work by not just propagating a value through a neuron, but by propagating an expectation and variance of a random variable. The detailed description of these models goes beyond this lecture, but please read up on this, for instance in Justin Byers' work from 2013 to 2015. The above very shortly highlighted some very popular modern types of neural networks. The end of the development of such models is most likely not yet near. So now you may want to start playing with your own neural networks. We suggest that you program your own neural networks in Python, and that's quite simple, but a normal implementation in Python is not very efficient. To get an efficient implementation, you may want to use one of the many public domain libraries, for instance Theano, which is available for any computing platforms, or TensorFlow, currently not available for Windows, but that should be coming soon, or something like Chainer.